Okay, so let's continue where we left off. Next, what we're gonna do is apply PEFT for the fine tuning. So, okay, this line is a key step in preparing a quantized model for the parameter efficient fine tuning or PEFT. And the purpose of it, or transformers integrated QLoRA setup, adapts quantized model, especially 4-bit or 8-bit loaded. And this is so that it can be fine-tuned using adapters like LoRa, which is what we're going to be using mostly. If you don't have this, your training might fail. It may fail, or it may give incorrect results, especially in low precision setups. What it does internally is it enables gradient checkpointing, model gradient checkpointing method. And it reduces memory usage during training by recomputing activations instead of storing them. Essentially, for large models plus quantized training. Okay. All right. So let's create a PEF config that we will need to pass to the LoRa. Let's create a LoRa config. Let's create our LoRa config. Okay. So let's go over each of these parameters. This line creates a configuration object for low rank adapter or LoRa, which is used to fine tune the model efficiently. And this is done by injecting trainable low rank adapter layers into the original model. This is part of the PEFT ecosystem, which is from Hugging Face, and typically it's used alongside quantized model to enable training on consumer GPUs or with limited memory in my case. And the purpose of this creates a low config object that really defines how and where LoRa adapter will be inserted into that base model that we will be fine tuning. And then now it will later be used into a function called the get PEFT model. So given the model and we'll get into that later on. The R8 parameter, what this does, it sets the rank of the LoRa adapter matrices. Just without getting too deep into the mathematical aspect of this, just think of LoRa as decomposing a large weight update matrix into two smaller matrices. This drastically reduces the number of trainable parameter. Okay, large matrices into a large weight matrix update, a large weight update matrix into smaller matrices, which drastically reduces the number of trainable parameters. With R equaling 8, what we're doing is adding only a small number of extra parameters per target. The LoRa alpha, we're going to set that to 16, and that's just a scale factor for LoRa updates. the output of the low rank adapter is scaled by the LoRa 16 divided by this rank, which results to be 2. And it's just a scaling factor. What this does, this helps balance the contribution of LoRa adapters within the frozen pre-trained weights. Now, for the target models, these two target models, what this does, this specify which layer in the model to inject LoRa adapters into. For Llama and other transformer models, this usually includes these two, which is query projection in attention and V projection in attention. So these are often the most important layers for controlling attention behavior. And if I haven't mentioned this before, attention is part of the architecture of LLM. So it's not the general definition that it's used for in a daily conversation. Okay, so don't try not to confuse it with that. So adapting, and this is that's for individuals who are relatively new to LLM. So anyway, so adapting them gives good performance while minimizing trainable parameters. We set the LoRa dropout at 0.05. What is that? This adds dropout only to the LoRa adapter layer, not the base model. Regularization to avoid overfitting during fine tuning. For the bias, we're going to set that to none. That controls whether to apply LoRa to bias terms. Other options include all and also LoRa only. None just means do not adapt bias terms, which is common and keeps training efficient. Task type is, we're going to set that to casual LM. And this just tells PEFT what type of task we are doing. In this case, casual language model, which is simply that is predicting the next token in a sequence. This just ensures proper integration with models like Llama, GPT, and others. Okay, so that's our LoRa config. So as I mentioned earlier, we're going to take the model, the base, the model, the LoRa, the pre-trained model or the prepared model, sorry, and the configuration, the LoRa config, and we're going to pass that to this model here, which is, it's going to return a PEFT model. So this line is really the final and critical step in converting the pre-trained model that we're using into a LoRa enabled fine-tunable model using PEFT. So you had the original model, you get the model from the pre-trained model, and then you prepare it, and then you pass it to LoRa to get a LoRa enabled fine-tunable model using PEFT. What this does, this function here just wraps the base model with LoRa adapters as defined in the LoRa config that we created here. The original model parameter remains frozen, and when it says frozen, when you train a model, you can freeze all or some. So and when you're training, the more you freezing it just means that you're not going to mess with it, you're just going to leave it. Okay. So the original parameters remain frozen. Only the injected low rank adapter layers become trainable. Okay. So this enables efficient fine-tuning even on large LLMs. This results in using far less memory and compute resource. Why do we use this method here? This transforms our quantized or full precision model into a LoRa enhanced model that one keeps original model architecture and weights intact, adds trainable adapter weights only to the layers we specify. And in this case, we only specified these two layers. This reduces training time, memory, and risk of catastrophic forgetting. All right, so I won't get into the internals, but at a high level, find target model, inject LoRa, freeze, wait, add, train it. Won't get any deeper than that. I think I got deep enough into that. One thing you can do, which is optional, but I'll just give you you can always inspect the trainable parameters for that model. So you just print this out. Okay, so let's set up our training configuration. And that's the training argument that we'll need to. Okay, so let's just do each of them. Let's set up each of them. So first we're gonna provide the output directory where I want the models to be saved and logs. And then we're gonna set the per device training. We're gonna set it real small to 2. So small batch size due to LLM memory requirement, and I'm low on that. And then I'm gonna do the same thing for eval. All right, and let's evaluate a larger batch size. So let's set our gradient accumulation step to 4, and we're gonna set epoch to very low. We're gonna just set it to 3. If you have a lot of resources, you can set that higher. And let's set the learning rate to 0.0002. Okay, and we are going to use half precision for training. So let's set our FP16 to true, and our eval strategy, let's set that to epoch. Let's do it on an epoch basis. And that's just what that does, is evaluate and save model every epoch. And let's do our step at 5. Should be good. Oops. Set that to 5. And let's just do our save strategy at 5 also. I mean epoch. Report. We're not going to do any reporting to WNB and other stuff. That's, you can explore those. Trying to make this as simple as possible. And login directory and push to hub. We're not going to push it here. I'll show you how to push this to Hugging Face outside of all of this functionality. I'm going to just separate that capability from here. So let's explain each of these real quick.